Hello everyone, and thanks for joining today's webinar on wind loading simulation for structural design. Today with me is Darren Lynch, our senior application engineer for AEC. He's joining us and showing later a live demonstration on the SimScale platform on the use case that we're talking about today. And he'll also join us during the Q&A session at the end. My name is Richard Zöke-Schuller, and I'm product manager for AEC, so architecture, engineering, construction at SimScale. Before we start, I want to make sure that whenever you have questions during the webinar, please post them into the questions section in the tool, and we'll have a couple minutes at the end where we try to answer all of your questions. So let's start. For the people that might not have heard about SimScale before, a quick introduction, who we are and what we do. So SimScale's motto is make simulate early, simulate more, and simulate ideally now. So we want to make high fidelity engineering simulation technically and economically accessible to everyone and at any scale, and by doing it in the cloud. So with our cloud-powered environment, we can make the simulations accessible without any local installation. Just access simscale.com via your browser and you can get started. We want to enable engineers to simulate without compromises, so you can use high accuracy simulations at a very fast speed and do the full design space exploration by running simulations all in parallel. The focus on SimScale is definitely on user experience and easy access to complex simulation technology by having a streamlined user interface and also in-tool support live at any time. Today, we want to focus on wind loading and facade pressure evaluation in the urban environment. Besides that, we have several other applications in external dynamics for buildings that can be done on SimScale. Just an overview here on the left side. One of the main applications that we serve today is pedestrian wind comfort on SimScale, where we can do a yearly assessment of the pedestrian wind conditions in an urban environment. But also we can go up to the full city scale models and also do high-rise wind loading applications on SimScale. So with today's webinar, we want to show you different strategies that you can apply to do wind load assessments and calculate the mean, but also the fluctuating part of the wind loads on buildings, facades, and solar panels. We will take a look also at a standard industry example for facade pressure and wind load evaluation, and have also with Darren a live demo on this case on the SimScale platform. So after today's webinar, you should know that with SimScale's virtual wind tunnel application, we can do fast and accurate modeling of turbulent flows in urban environments. We can evaluate the mean and the fluctuating wind loads on the full building or on facade elements by using transient CFD capabilities. And we enable engineers that work on complex buildings to use SimScale's GPU accelerated solvers for faster design decisions and iterations earlier in the design process. Let's take a step back and first think about why structural wind load assessment is important. And among many different aspects of building design, the two where it really boils down to for a wind load assessment is safety on the one hand and sustainability on the other hand. Right, and they're typically pulling in opposite directions. So for safety, we're concerned, for example, on the occupants inside the building. So definitely we want to make sure that during extreme weather conditions, the building won't collapse, but also that facade elements won't rip off the building and hurt people in the surrounding of the building itself. On the other hand, we want to ensure that we have a sustainable built environment. So For example, we want to reduce the embodied carbon inside the mass of the building itself, or we want to optimize and minimize the energy use of the building by employing natural ventilation strategies, energy harvesting within the building, and so on. And within these two different spheres, we want to look at the optimal design that typically lies between these two extremes that ensures safety, but also is the most sustainable design possible within the constraints given. And a wonderful example for exactly this is given by this case study of our customer, Adrian Smith and Jordan Gill Architects, where they did early massing design optimizations on a high-rise tower. So starting on the top left with a simple cuboid building and optimizing iteratively through different design options while tapering, adding steps inside the building, and also in the end notches to reduce the wind load in the end by 35%. What they also could do while using SimScale is additionally add wind relief to further reduce the wind load by 5%, and also evaluate the potential to include vertical axis wind turbines into the building itself and estimate about 181,000 kilowatt hours per year energy production through these wind turbines from the building itself. For more details, you can go to simscale.com and have a look at the very extensive story that we have on our website on exactly this case, which really combines both aspects in one use case. Now, taking a little bit a deeper look on what matters when looking at wind loading on buildings in the urban context, we have to talk about the atmospheric boundary layer behavior. So how the wind behaves close to the surface and up to about a kilometer high in the air. So here the mean wind speed is typically following a logarithmic profile, but along this mean, there's a lot of fluctuations in the wind speeds locally and with time. So when we look about the mean wind speed with the height and take a particular point, let's say 50 meters from the ground, and we can see here on the right bottom side what a typical signal for the wind velocity at this height would look like. So we see there's a lot of transient effects going on in this particular point, and the fluctuations happen along a mean value. And for wind loading applications, that these fluctuations and the actual peak values of these are the important factors that decide the actual wind load, the design wind load that we have to take into account to design our building for. So now, what methods do we have in place to actually design buildings for different wind loads and evaluate the wind loads? Just presenting here the three main options that we have. First of all, codified analytical calculations that can be found, for example, in the Eurocode or the Australia, New Zealand structural design actions or the ACE 7 to 10 minimum design loads for buildings and other structures. So these have basically analytical models to estimate structural wind loads on mid and high-rise buildings, and they're really well suited for standard building shapes. Looking at the benefits and limitations, they're very cheap. You can run it in an Excel sheet. They're relatively fast if you're really experienced in what you're doing, and then they're following a standardized approach, and they're approved and a certified method to evaluate wind load. On the other hand, there are several approximations that are done within these calculations regarding the building shape itself, the surroundings, and the wind effects themselves as well. And they usually lead to relatively conservative results, meaning higher loads than what is typically observed in the reality. The second option, and also very widely used, are wind tunnel experiments. There are various providers worldwide for atmospheric boundary layer wind tunnels that can do these kind of experiments. They're also certified for mid to even high-rise buildings, typically done only late stage as a final verification, but they also can take into account complex building shapes. These are also very accurate and follow standardized practices, and are also an approved method to evaluate wind loads. On the other hand, the limitations or the drawbacks are it's typically very expensive compared to the other alternatives. It's a long turnaround time from end to end until we have the final results in. And they're only feasible due to the high cost in the late stage, so they're not ideal for design optimization. And then as a last option, relatively new, is transient CFD analysis using LES simulation. These are ideally used for design optimization and early to mid-stage design stages. And the main purpose here would be to reduce potential wind tunnel iterations. So these are very affordable and fast compared to other options. They are ideal for design optimization, and we can get more design insights than we would get with, for example, the codified analytical examples or even the wind tunnel, because we have the full 3D results available at any point and any time. But they're usually not yet approved for wind load certification. Now, let's take a look at how such a CFD wind study would look like. And here we're looking at the standard CAARC building. So it's a simple cube-shaped building, 45 meters wide and 180 meters high. And we're putting this in a virtual wind tunnel. So here we are having the same geometry that you would have in an explicit wind tunnel, but we're all evaluating then the wind conditions virtually. So here on the top left, you see a typical discretization of the mesh that we would have in the wind section plane. So what we show here, first of all, we need to ensure that the wind profile that we're getting out of this virtual wind tunnel with all these roughness elements and so on is actually the same as you would have with the other alternatives. So the analytical target profile for the atmospheric boundary layer, which we see here in the left. So following this logarithmic profile, and with the black squares, the results that we would get with an experimental wind tunnel. So here we can see that for the mean values, we exactly match the reference. And also regarding the turbulence quantities that are a measure for the fluctuating part of the wind, we also match reasonably well with the wind tunnel experiments. Now we have the wind tunnel itself, and the next step would be to putting the actual building also in the wind tunnel, and then evaluate the facade pressure and the fluctuating parts on the facade to evaluate the wind load on these facade elements or the building itself. So these results that we are seeing here can be directly output on the SimScale platform. So we can get the CP values, for example, the pressure coefficients. That's a standard measure you would get out of either wind tunnel experiments, but also the CFD analysis, which show on the front side a high pressure region, more or less in the center line of the building, above 3/4 height. And then we see negative pressures on the side and behind the building. And here you see on the right side the typical results you would be looking at in standard publications about this case, being the mean CP value around 3/4 or 2/3 of the height of the building, and also on the lower end the fluctuating parts of the pressure coefficient and the same points. So we see that that the fluctuating part is a little bit higher, but same order of magnitude than the mean value itself. So that already shows us that the fluctuations here play an important role to assess the overall load on the structure. Now, enough of pictures itself, so let's go to our colleague Darren, and he'll show you how this exactly would be done on the SimScale platform.
So this is a small 10-minute demo of the SimScale platform where we get to show you some cool things about SimScale. As Richard mentioned earlier, it is a browser-based cloud simulation platform, which means that we can actually access, set up simulations and do pre-processing all within this browser space without having anything locally installed or any amounts of local hardware available to you. So in terms of user interface, we've got this large viewer in the center where we're at the moment looking at some transient results from the simulation that we're going to be looking at. On the left hand side, we've got the simulation tree, which is where we do all the technical setup and select what we're going to be looking at. And on the right hand side, we've got the geometry tree. So this is where we look at any of the parts of the geometry that we've uploaded to the SimScale platform. And perhaps more importantly is the chat functionality on the right hand side there. So if you've got any questions throughout any part of the SimScale platform experience, you can actually ask them here and get live support from our team. So without any further ado, let's talk about the case on screen. Now, as we have been looking at throughout the rest of the webinar, this is the CAARC building. And this particular case has actually got the tool building within a context. And this context was taken actually from CAD Mapper, which is a great online source. I really do encourage you to check it out. Now, what we're actually going to do here is we're going to talk through the main steps that is required to actually obtain some wind loading results from the SimScale platform. We're going to start from the top, work our way through, and at the end we're going to show some of the key results that we have also looked at in the previous parts of the presentation. What we're actually going to do here is we're going to talk through the main steps that is required to actually obtain some wind loading results from the SimScale platform. We're going to start from the top, work our way through, and at the end we're going to show some of the key results that we have also looked at in the previous parts of the presentation. So the first thing that we're going to do to start up one of these wind loading simulations is to upload a geometry. And geometry uploads can be done in this area here, where we can drag and drop geometry or find it on our computer. And you can see there's a lot of native file formats supported, including Revit and Rhino. However, for external building aerodynamics, the most robust file format is probably the STL file format, and therefore I recommend you use that. Once this has been uploaded, you'll see it in the visualizer here, and we can inspect the geometry, and from here we can actually create a new simulation. Now, today we're going to concentrate on the incompressible LBM simulation. Before, we've been using the pedestrian wind comfort for microclimate analysis. However, for this more expert use case, we want to be using something with a bit more control, and therefore we are selecting the incompressible LBM. So I'm going to give you a very high level guide to setting up one of these simulations. This is generally a checkbox type workflow where we start at the top, we work our way down, and when we get to the bottom we're actually ready to start a simulation. I'm not going to spend too much time on every single input. I'm just going to go to a few of the key checkpoints in this setup. So firstly, I'm going to start with the external flow domain. I do encourage you to go to our documentation pages and check out some rules of thumb to setting up these sizings, or you can check something that's a bit more in-depth, such as cost 14. Now, what you could also do here is very cleverly change the rotation angle. So if, for example, we wanted a northerly wind direction, it would be 0 degrees. If we wanted a northeasterly wind direction, maybe it's minus 45 degrees, and so on and so forth. And we can use these rotation angles to very quickly vary this wind direction in our simulation setup. The next major thing that we really need to do to set up one of these simulations is come to the velocity inlet condition. Now, advanced users might want to set up this boundary condition based upon a custom boundary condition or a custom atmospheric boundary layer. And this can be done by defining all of the parameters, velocity, turbulence intensity, and dissipation rate as a function of height. And this can be done by CSV files. Alternatively, however, if you're happy using the log law formulation, then you can use this atmospheric boundary layer inlet condition, where we simply define reference velocity, reference height, and the roughness, for example 0.5 meters. So once we've defined our flow domain, our wind tunnel, and also our inlet condition, the atmospheric boundary layer, we also want to tell the solver how long to run the simulation for and what to export as a result. And this is done in simulation control, where you can define the end time. Typically you want 3 fluid passes to be defined here. And we can access the result control, where we can get some typical outputs such as the forces and moments on the building, probe points, this could be tapping points on the building, or statistical averaging, so for example the average pressures on the surface of a building. When you're ready to start a simulation, we can come along to simulation runs, and we can press the little plus button down here. Now at this point it's going to check your setup and do a sanity check, and it will tell you anything that needs to change before a simulation can be run, or alternatively gives you any advisories that it thinks you could do to improve the simulation. In this case it's given us no errors, and it's given us no warnings, which means there's nothing for us to do and the simulation is exactly how the solver expected the inputs to look like. So we can go ahead and start a new simulation. Now of course, as many simulations as you need to run can be run at the same time in parallel. So for example, if you've got 8 different wind directions that you want to test all at the same time, then you can absolutely go through and do that. For example, I can come back to flow domain, change the angle, save it, and start a new simulation. And you're going to get all of these results back at approximately the same time, because they're all run on individual instances. None of the runs that you've got currently going are going to affect any of the other runs, which means this is entirely a scalable solution. And when the simulations are done, we're going to get a little email back to say, hey, your results are in, come and check them out. So when we've finished the simulation and we've come back to check our results, you should see something like this, where your simulation has got some runs, and each one of these runs has got one of the outputs that we talked about earlier, so whether that be transient, average, or snapshot outputs. Additionally, any other outputs that you might have asked for. In this case, we've got some probe points for the validation points on the surface of the building. And you can actually select any of these outputs to actually navigate to those results to visualize them in the viewer. In this case, because we've got a static atmospheric boundary layer applied to the simulation, it's going to be most relevant for us to be looking at the average solution, which is what I've got here. And you can see that I've done a quick calculator function. You can just type in a few things onto the calculator function to actually obtain the pressure coefficient from the pressure values. And we can see that in the viewer scaled between -1 and 1, where we would expect on the windward side to have a peak pressure coefficient of approximately 1, and on the leeward side somewhere just below minus 0.5. Now, apart from pressure coefficients, we have of course got all of the other typical outputs from the simulation. You can check Y+ values, you can check turbulent kinetic energy. If you were looking at flow fields, for example, I might want to look at a vertical slice. I could also look at a velocity profile as well. Here we go. So maybe in this case, instead of pressure coefficient, I want to look at velocity magnitude, and the viewer would react accordingly. Here we go. So really quite a few things that you can do with the post-processor to build up your understanding of these results. And of course you can change the scales. You can even have these as continuous scales as well. And of course, these results can be downloaded. So if you've got need for some more advanced post-processing, some automated post-processing, these can either be downloaded from the platform by right-clicking or accessed via the API as well. So now I'm going to hand back to Richard to the question and answers discussion that we're going to have. Hopefully you've been writing in your questions in the chat functionality. If you haven't, no worries. May quickly ask any questions that you've got down now, and we should be able to address them before the end of the session. Thanks very much for watching.
Thanks, Darren. Great presentation. Okay, so before we look at the questions, what is the next steps? I think we have several ways how you could reach us. Definitely visit simscale.com, check out what we have to offer, create an account and log in. You can also directly send us an email at sales@simscale.com, ask your questions there, and let us know what you would need from a CFD solution, and we'll get back in touch with you. Also, have a look at our webinars page, which we have here. So we have a lot of webinars where you can also watch past webinars, recordings, or sign up for the upcoming webinars in the next weeks and months. So now we have a lot of questions. Let's get started. How is the inflow turbulence defined in the current case is the question. So we have seen several cases here. The case that Darren has shown in the live demo didn't have any roughness elements that you would have in a wind tunnel. So here we applied the turbulence profile with the height directly with the mean profile, also the velocity profile. So in this case, you will have a mean velocity inlet and a mean turbulence and turbulent dissipation with height. So in this case, you would not have the actual fluctuations directly in the inlet yet. For that, you would need to model the roughness elements as it's done in the wind tunnel for now. So maybe that's something we can already talk about. We are working on a solution where we can basically strip down 3/4 of the simulation domain by not modeling actually the wind tunnel roughness elements explicitly, but having a solution that would already at the inlet provide us with the correct mean, but also the fluctuating parts of the flow according to the specifications of the exposure category and the inflow type that you would like to have for a specific case. And then we can save also a lot of money on the simulation side as well as time.
Perfect. I've got one here that says, you write CFD is affordable and fast. What is the necessary time and cost for a 36 wind direction wind load on a building? Also, what is the typical experimental wind results? That is what typical experimental wind tunnel would deliver in 2 to 3 months. So I can kind of piggyback what I said in the demo. It took about 7 hours to do one single wind direction, but this is entirely a scalable solution. So it will take 7 hours for each individual wind direction. You can absolutely solve each direction individually in parallel. So 36 wind directions all at the same time, not a problem. Additionally, if you're interested in the cost for running these simulations, this will very much vary in the complexity of the buildings, the context, and also the simulation you're trying to run. If you want more information on the costing for SimScale, then please reach out to sales@simscale.com. Much appreciated. And very conscious of the time, Richard, there's probably only time for another couple of questions. Have you got one in particular that you want to answer?
There's another question. Can this be used to simulate violent wind events, tornado and hurricane? Yeah, that's a good question. That's actually out of the scope of what we are doing here, right? And also out of the scope of most of the traditional wind tunnels, right? So these extreme events have very specific conditions on how the wind behaves in this event, not only locally but also with the profiles and so on. So the conditions, what we are looking here is maximum wind speeds that occur within a 50-year period, under storm conditions, but not hurricane or this type of specific storm situations. For this, this approach is not really specifically suited.
Excellent. Yeah, I've got one that I've just lost. Have you benchmarked your results? Maybe check the fluctuating pressures rather than the mean. And please remember to reference the people's work that you are copying. Absolutely, we have benchmarked these results, and we are actually quite impressed. And of course, we wouldn't publicize anything without anyone's permission. I do hope we can obtain some permissions in the near future to show you these results. But in the meantime, we've actually got a catalogue of validation studies on our website that you can check it out off the shelf today. So please check that out in the documentation pages. Any other questions from you that you want to answer, Richard? Maybe one more?
Yeah, there's a question if you can automate this in Rhino Grasshopper. Yes, we can do that. Definitely, we have an API where you with which you can access SimScale. So besides that, we have already a plugin in the works where we work together with Tom Massetti on a Rhino plugin for a virtual wind tunnel. You can reach out to us directly if you're interested in knowing more and maybe participating in a beta program. So I would be happy to enable this for you, and you can check it out yourself. Yes, I think we are already out of time. Unfortunately, there are more questions to answer, but I think that's it for now. Yes.
I think any questions that we've missed, we record all these questions and we'll get back to you post webinar as well. So not to worry if we haven't answered your question, we will go back to you.
Exactly. Okay, then thank you again for your time for joining, and hopefully we'll see you again in one of the next webinars. Until then, have a good day and bye-bye.